So we have Alessandra Frabetti for our next talk. Who's going to talk about quantization in covariant field theory with Poisson algebra bundles. And so I just asked Alessandra very quickly what her trajectory was. I've known her for maybe a year plus, almost 2 years, over various conferences. But I don't know exactly her trajectory, but I did ask her, and she said she started off her PhD in Italy, but then moved to Strasbourg to finish her PhD in mathematical physics. And then she did a postdoc in Strasbourg, and in Italy, and then in Switzerland, in Lausanne. And then she got a position at Lyon. So
thank you very much. And I would really like to thank a lot all the organizers, because this is really a very nice event. I'm very happy to be here, and in particular to be in India. I came here in '98, and so it's a long time, and I really like it, enjoy it very much. So thank you a lot. Okay, so I'm going to give a talk which mixes up algebra, geometry, and analysis at the end. And I'm going practically to skip all the details in the three fields. And it's motivated by QFT. So it's a joint work with two colleagues in Lyon. And we built up a small network in mathematical physics in close to Lyon, so two other cities in France, Dijon and Metz. And so there is a whole program around this. This is the starting point of a program with a lot of people involved. So I'm trying to sketch what's the idea of this. So I start with the idea, the basic idea underlying this. So the aim here is to realize QFT as a deformation of a classical covariant field theory, so by preserving covariancy. So preserving covariancy for for relativistic field theory is an old problem, which was settled by physicists in Poland in the 70s. And there are many people who worked on that. And this was the beginning of a lot of different theories. Among them, there is multisymplectic geometry. And nowadays, there is Lagrangian field theory, which is somehow majored by Christian Bloman in Bonn. I think algebraic or axiomatic quantum field theory also is of the same sort. It's a field theory which aims to preserve covariancy from the very beginning. So for me, from the point of view of geometry, preserving covariancy means always keeping track of the bundles where the fields start from. When we lose the bundles, somehow we lose the covariancy. So the possibility to act with groups, like the Poincaré groups on the manifold, or gauge groups on the fibers of the bundle and on the fields, and so on. So the aim is to keep track of the bundles. And the idea here is to keep track of these bundles also during quantization. And there is a tool which is used in algebraic quantum field theory, in perturbative algebraic quantum field theory, which is to quantize by deformation. Okay, so there is a star product, we already heard about it, and I'm going to present another kind of deformation. So the idea, I take the toy model 5-4 theory. Just to give an example, the correlation function, so I don't know if I can, yeah. Okay, so the correlation function for interacting fields, so this is the ground state for the interacting field. This is just how it looks like the definition in Peshkin-Schroeder book, okay? One needs to compute in the vacuum ground field the time ordering of the fields with the interacting Lagrangian in the exponential. Okay, and take out some part here, which is just the empty, the vacuum graphs. So it can be, so the exponential here can be expanded. It gives rise to products of propagators, And since we are time ordering these operators here, the propagator we need to use here is the Feynman propagator, which is not the propagator that Kasia was mentioning yesterday. It's the sum of the retarded and advanced, not the difference. So it's a symmetric propagator. Its wavefront set is much worse than the Whiteman propagator. And this is what causes all the problems of renormalization, after all, in this time order. So if we go to Feynman graphs, all this expansion here, this amount to the free propagator plus something in the power lambda square. Lambda is the coupling constant. Of course, there are h bars inside, which are in the loops. And then there are higher terms. And all these factors here, which appear here, which come out of the exponential, the explicit computation, they are just hidden in the symmetry factor of this graph. Okay, so now I propose to go. Yeah, please.
Yeah, I mean, obviously that formula doesn't make sense, right? Like these products of operators, like 5 to the 4, that doesn't make sense as a product of operators.
Yes, so yeah. This is, yeah, sure.
Yeah, so that formula doesn't make sense, but it can actually be made precise. So it's not just a picture. So yeah, I mean, the combinatorics of that formula still exists, although these cannot be made really precise as products of operators.
I'm skipping all the analytical details here because just to give the idea, okay, so at the end of a lot of work, one gets a certain Feynman expansion here. And now I want to go back and see what is this? This in fact comes from the expectation value on the vacuum of a certain operator. So let's go, if I can, okay. So I can try to read this here as the amplitude of a classical deformation. That's my point. So I propose to change the meaning of the Feynman graphs and to read them in a classical way. So where there are propagators and between points, I take the time-ordered product of fields computed at the points. So this is kind of automatically done almost everywhere. But if I do this, then inside here, I have something which is really classical. Now, these are not operators. I can read them as truly fields computed in points. And then at the end, I need to apply this map here, which gives me the amplitude. Okay? In fact, the point is, what is this amplitude here that I can apply to the classical deformation in order to get something quantum? And what is the deformation which is inside here on the classical level? So on the classical level, now I'm going to fix the starting point here. There are just classical fields. And I'm going to sketch what is this quantization, in which sense. And then I will explain what is the problem on which I was stuck for 15 years, in fact. And that, yeah. Sorry?
If these are just functions, what is the meaning of the expectation value?
This is part of the question, in fact. I needed to explain what is this deformation and what is this expectation. Yeah, okay.
I guess the question is, which part of it is classical that you said?
Okay, so once we compute the expectation value, we are in the quantum world. Okay, we get an identity for the correlation function. So this is quantum, a quantum expectation. Okay, what I'm proposing is to compute it as the amplitude of something which is classical.
Yeah, maybe I can try to give a response to Dimitra. So if you think of these as functions, and you think as this expression in the middle as some functional of fields, classical, it's all classical, then this expectation value quotation marks could be, I mean, it is in this case, evaluation at 0. So you compute these time-ordered products as Alessandra is going to show, and then you evaluate at phi equals 0, you get a number. And that number computes that quantum amplitude that is sort of, not so well-defined, let's say, but the classical thing that she's going to show is well-defined. But yeah, think of it as evaluation at zero of a classical thing. Does it make sense? I think that makes sense.
No, I think Kasia has already an interpretation which is very practical. I'm going to fly on algebraic structures before coming to her. Okay, so I start with the easy part, which is already done, which is the quantization procedure. So let's start with the mathematically, what is the background of the deformation I'm going to use? It's what is called the twist deformation. You can find it in a paper by Swidler in '68. It has been used by people doing combinatorics in the United States by Giancarlo Rota and all his school in '87. So there exists in a version which is combinatorial version. And there exists the Hopf algebra version of that, which is due to Dreamfeld and to Manin. So Manin is the one who invented the circle product. Dreamfeld was talking about deformation, quasi-triangular Hopf algebras. Majid was also working on that. So there is a real community in mathematics of people and in mathematical physics dealing with such deformations. Okay, how does it work? We have to start with a Hopf algebra. So Hopf algebra, I realized that nobody said what a Hopf algebra is. So I decided not to add on the slides, but a Hopf algebra. So if you start with an algebra, then you have a product, everything which is linear. So this is a tensor product among vector spaces, which is associative. It can be commutative or not. And there is a unit. The unit goes from the scalar, so the field, to A. So the image of the unit in the scalar here, U of 1, is going to be the unit in the algebra. And they satisfy a lot of axioms. So one can dualize these maps and get co-algebra. So a co-algebra is a vector space, C, with a coproduct, which goes from C to C tensor C, and a co-unit, which projects everything to the scalar. And it can be co-associative, co-commutative if we wish. And there are a lot of axioms which are dual to this one. So and then one can take the two together to have a Hopf algebra. So it's a vector space H which has multiplications, co-multiplication, plus an antipode, which is a map which goes from H to H, which satisfies a lot of compatibility with the two I don't want to say. So the important point is that usually multiplication, we use them to branch together things, elements. So we want to have a single element out of two that we are giving. And here the coproduct takes an element and splits it in pairs. So if we have something which is already a product of something, or it's generated freely, so it's A times B times C, whatever, with this coproduct, I can go back and find the constituent elements of this. So there is a Swidler notation for this, which is something like that. So, and usually this sum is omitted. So once you have a coproduct, an element can be split in two parts, and they are labeled by 1 and 2. And the co-unit does the opposite. So I will skip the co-unit. So you have an element, and you are going to have a scalar out of this element here. These two structures are very important in my construction. Okay, so given such a Hopf algebra, which must be commutative eventually in the graded sense, so a symmetric or a wedge product, so an exterior algebra. There is a notion of two cocycle or Laplace pairing, which is a scalar map with two inputs from the Hopf algebra, which satisfies this rule, which mainly say that on the units, we go back to the scalar given by the co-unit of the Hopf algebra. And if you have a product on one side, then on the other side, you split it with the coproduct, and then you apply the Laplace pairing on both sides. So this allows to reconstruct the value of this Laplace pairing on all elements which are of type products, so from the generators. Okay, so given this structure here, on H, one can define a twisted algebra. So deform the original product into a circle product, which is defined in this way. We take both elements, we split them up with a co-product, and then one copy is paired to a scalar with the Laplace pairing, and the other part is multiplied. Okay, this circle product, then it's clear, it's defined recursively because of the properties of this Laplace pairing and the coproduct, which always splits elements into its elementary components. Okay, so how do we apply to QFT? So this work was done long ago with Christian Bruder, Bertrand Fauser, and Robert Oeckl in 2004, and then Christian Bruder really exploited it deeply. There is a wonderful paper in 2009 where he constructs Feynman graphs using these tools. Okay, so let's take free fields.
Since you're showing the names, it would be good to mention also other people who have done it earlier. So like this idea of QFT as a twist, I mean, literally this thing appeared in works of Dutch and Vrenhagen from 2000. So
not twist deformation.
Yeah, but
let me say it, and then
it's nice to also mention other people. It's not just done,
but it's not the same.
Yeah.
It's not the same deformation. We can talk about it later. Okay, so we start with the free fields in the very non-mathematical sense that we take the free commutative algebra, so the symmetric algebra on all objects of type phi to the power n of x, where x is any element of the space-time, and phi, sorry, I'm missing, okay.
Excuse me.
Yes, there is.
So when you defined a Hopf algebra, you just said there is an algebra and then we have a co-algebra structure. But why did you say in the slide that there is a grading? Is there any kind of grading that is?
You can consider a graded algebra instead of symmetric. Here it can be graded symmetric, so you can include bosons and fermions inside.
Okay, so
it's a graded symmetric, not necessarily commutative. It can be graded commutative.
Okay.
Okay, so let's take this. This is the problem. This algebra, it's spanned by this object phi to the power n of x, where n phi is a field, and x is any point in the space-time. And then if you choose this Laplace pairing, you will get circle products. So there are two obvious choices. You can either consider the Weidmann propagator, and what you get as a circle product is the operator product, and this was already existing in this shape in physics, I do agree. And yes, in mathematics, I said it, yeah. And there is the Feynman propagator. If you choose the Feynman propagator as a Laplace pairing, then you get the time-ordered product as a circle product, okay? And the expectation value, so this amplitude is just the co-unit applied to the product. So the algebraic structure fixed here is enough to recover the expectation values as we want them. So, okay, this was clear from the physical point of view. It really recovered the usual theory. So this is done first for free fields, and then you can add the interactions. So the interaction, if it's polynomial, you can just plug it inside and insert it in the co-unit here, and then you get explicit Feynman graphs. Okay, and the renormalization comes with the powers of the field in time-ordered product. This makes a problem, and so this was solved later by Bruder-Schmidt, who needed a second Hopf algebra structure just on the generators, this phi n. So phi n is in fact phi multiplied by phi n times. So it can be reduced to other types of generators, just a single fields, and they needed a second coproduct on this. And there is an alternative version, which was proved by Herskovich in 2019, by introducing two different tensor products directly on the sections on these fields in locally convex vector spaces of sections. And he uses the existence of these two different products in order to code the renormalization. Okay, so somehow the quantization is given by this procedure. The problems are, first of all, it's formally consistent, but what is this algebra? In fact, what is this symmetric algebra spanned by these objects? Geometrically, it doesn't make sense. And then what is, from my personal perspective, I was working on renormalization of algebras, and I would like to understand what is the intersection with that. Okay. So let's start with classical data that you can find in Kasia's book of a vector bundle over space-time plus a Lagrangian. And let's consider the set of fields, which are smooth sections of this bundle, and the set of fields satisfying the Euler-Lagrange equation. So observables, on-shell observables are functionals defined on the set of fields satisfying the Euler-Lagrange equation and giving real or complex results. And then we can find this algebra as a quotient by a certain ideal. So we can start by studying the off-shell algebra and construct the on-shell algebra of observable later on. So both are all algebras with a multiplication, pointwise multiplication of functionals on the fields. And one can define the Poisson bracket, which is just the Paycha's bracket using the causal propagator defined by this Lagrangian here. So this imposes conditions on the manifold, which must be globally hyperbolic, and on the Lagrangian, which must give a set of hyperbolic equations in order to have this causal propagator. Okay, so my point here, so this is all known. It's very well described in Kasia's book, for instance. My point is, can I realize these observables using sections of bundles? Which bundles? So let's start with local observables. Local observables are of type integral of something which is integrated over the space-time. And so since my fields phi have value in a vector bundle, I need to pair them to something with values in the dual vector bundle. Otherwise, I don't have scalars and I cannot make the integral. So local observables, which are of this type, they are represented by sections of the dual vector bundle. And in fact, we need to consider jets of the fields here, so fields plus its derivatives. Okay, so we will always have jets bundle instead of bundles. And if the field is taken to a certain power, which happens in the Lagrangian itself, for instance, then we need to consider as a pairing something which can pair to powers of the field, which are going to be powers, symmetric powers of the dual bundle. Okay? And then we take two such local observables, we multiply them with this commutative product, and we get multi-local observables. And these multi-local observables, they are two integrals, double integrals, so on 2 points, x and y. Okay, so they can be represented by something which is a section of a bundle on 2 copies of M. So this representation here, you can find it also in Kasia's book. The problem that I see is that if I want this observable here, this product to be represented exactly by this kernel, which stands inside here, which is a section of a bundle, then I need it to be commutative, because the product between the associated functionals is commutative. But so the external tensor product that one needs to use here is not commutative in nature. I cannot exchange the two functions, so it's not commutative because the 2 points x and y on the base manifold, they cannot be exchanged. So mathematically, what one has to do is to quotient out the manifold M cross M by the action of the symmetric group and consider what is the set of configurations of several points in the manifold. Okay, but if we do this, we get an obifold. This is where I'm saying that obifolds naturally arise here. And so in order to avoid the problems on the diagonal, just to see if the algebraic structure works, I took off the diagonal and what I get, and I quotient out later on. So I have configurations of distinct points on the manifold. So I have spaces of points of k points on the manifold. This is configuration spaces. Okay, and then the trick is that I know what is the tensor product I want. I have bundles here for these sections with the usual tensor product, which is pointwise on the same base point. And I have this external tensor product. And so the trick here is to really change the category of vector bundles in order to have this tensor product here commutative. So this is the trick I'm going to propose.
Yeah, so I didn't, so until now you've been talking about fields and sections of vector bundles or these other generalized bundles, jet bundles and so on, but where does K come from? What is the?
K is the number of points. Here I have 2 point.
As an endpoint function?
Yes, when I multiply two local functionals, I run into an integral over two distinct points. If I keep multiplying local functionals, I will need sections of bundle over k points.
You can think of this as distinct points on the manifold?
They are distinct points on the manifold, and this is a typical place where all these configuration spaces of different points, which were considered by many people, Kontsevich, for instance, and there are many others, they arise in topological operas, for instance, all these little disk operas with punctured points. These configuration points here, they come from this construction.
Sorry, I have another question. So, okay, so assuming that we really need to think of these things in terms of sections of a bundle, there's obviously some ambiguity because you can integrate by parts. So you cannot really say that your F1 and F2 represent these functionals on the left, because if you have a derivative, you can always integrate by parts.
No, the derivatives are done point by point, not exchanging points. Anyway, there is another.
But exactly. I mean, a presentation of a local functional in terms of integrands is obviously up to total derivative. It doesn't get better.
Sorry, I'm not saying that this representation is faithful.
Oh, okay.
Okay.
Then good. Then I'm happy.
Okay. It is not. It is not. And there is a plan, a working plan around that. Okay, so then my purpose is to show you what is the nice category of vector bundles which works to solve this problem. So in order to do this, I need to consider this configuration of points on any number of points. So I'm taking something that mathematicians working in higher structures call manifold. In fact, it's a disjoint union of an infinite number of manifolds, true manifold. They treat them as they were manifold, even if there are an infinite number of connected components. The good point in this whole configuration space is that you are always working on a finite number of points. So you're really working on a manifold, even if formally it is infinite dimensional. And we have the vacuum as a classical configuration. So the configuration on 0 point is an object. It's an element of a set, which is the space of 0 point configuration. So now that we have this, we can define structures on the vacuum. Okay, so for k points, I will denote the configuration with an underlying bar here and with a vector above if it's just a tuple. But here the configurations then are just finite sets of points where these points are not ordered. I can switch, there is no order. It's just a finite set. It's not a tuple, okay? And then I look at vector bundles. Yes, so they are going to be 2 by 2 distinct points because I took off the diagonal in purpose, not to have singularities at first.
The small diagonal or the big?
The large diagonal. I take off all diagonals. So they are really distinct points. Okay, then I consider vector bundles, which are, they are just vector bundles on every manifold, which is the k-point configuration, which is a manifold. It is not orientable in general, even if M is orientable. But vector bundles just make sense. Bundle maps are a collection of usual bundle maps with given number of base points, and everything works very well. And so there is a theorem on this. In this category, this category is an example of what people in species, so in combinatorics, call a symmetric two-monoidal category. There is a wonderful book by Marcelo Aguiar and Ramanujan in 2010, where they treat this in a very categorical way. In order to have a symmetric two-monoidal category, you need to have two distinct tensor products in your category, and which are compatible with some axiomatic maps. And this works here. And the two products, tensor products, are then between bundles. So the Hadamard product is just the usual round tensor bundle. A tensor product is just the point-wise tensor product. So it is fiber by fiber. It doesn't change anything. This is the usual tensor product of vector bundles. And the Cauchy, which is a square tensor product, mixes up the points in the configuration. So what I'm doing is I'm starting by a configuration. I split it up in all possible ways. So here is an example. On two-point configuration, I can consider the empty, the vacuum, paired to the two-point configuration, or I split X and Y in two different positions in two different ways, or the vacuum coupled with the other one. And on every configuration, I consider the vector bundle, and I take the sum of all of them. Okay, so the theorem is that this is truly well-defined symmetric two-monoidal category, and moreover, this Cauchy tensor product is really a symmetrized version of the usual external tensor product of bundle. So we can just try to read in this Cauchy tensor product what is usually done in QFT. This is on multi-local observables.
Excuse me, is there a functor from the monoidal category of bundles, vector bundles, to this symmetrized version? Is there a symmetrizing functor?
So these two bundles, these two tensor bundles exist theoretically in a two-symmetric monoidal category. And this is an example of such a realization. It's an example of a category where there exist these two tensor products.
So I think I was asking something else. From the monoidal category of vector bundles, can you build a symmetrizing functor which...
So there is a functor which goes from vector bundles over M to vector bundles over the configuration space of M. In fact, here we have just one vector bundle E over M, and we bring it to the, so it's vector bundle, so we take the null vector on the vacuum, E on M, and again, all the null space on the configuration smaller than 2. So it's 0 everywhere except on M. Okay. So algebraically, what I need to construct is the structure of observables, but inside the vector bundles. So I need, I'm sorry, this is an algebraic page. So I need to construct algebras compatible with two types of products, one with, so I'm in this category. So my algebras are vector bundles over the configuration space, always. So I consider such vector bundles endowed with two different multiplication, one with respect to one tensor product and the other one with respect to the other one, and with 2 units. And I can do the same for coproducts, and I'm not writing them, but I need both of them because of the Sweetler circle product. So I'm considering 2 algebra bundles and 2 co-algebra bundles. And as usual, I know that the dual, the linear dual, graded linear dual of a co-algebra is giving me an algebra. Okay, this is standard. And then I construct the free algebras and free co-algebras, just tensors, starting from generators. So if I start with one bundle on M, I can embed it in this, with this procedure on the configuration space, and then I can consider the powers with respect to these two tensor products given above. So I have tensor algebras or tensor co-algebras, so the co-free blah, blah, blah. And then I can quotient out by the symmetrization ideal to get symmetric powers with respect to one tensor product. And same for the co-algebra, I can have a usual co-algebra inside. And then I can do the same for the other tensor product, and then I combine them, and I finally get what I want, which is this bundle, which is constructed on the dual of E, by taking first the Hadamard symmetric power, so the usual tensor product. All this bundle here lives on M, and then I take the Cauchy symmetric product, and all this will live on the configuration space. And by construction, all this is the dual of a certain bundle of symmetric tensors, okay? I also need the Poisson structure. So a Poisson two-algebra bundle is a vector bundle, which is an algebra commutative with respect to both multiplication and with a Poisson bracket with respect only to the Cauchy tensor product. And it satisfies the usual axioms. I will not discuss the Leibniz rule with respect to the Hadamard product because this is really new. And I now have an explanation from this. It comes from a double Poisson structure that I've put in the appendix, but so I just don't comment. It's easy to just introduce what a Poisson algebra should be in this context. And the theorem is that given a vector bundle on M, by these symmetric tensors with respect to both tensor products, you immediately get a two algebra bundle, which is free commutative with respect to everything. And if you take an antisymmetric bundle map on the generators, on the two generators with values in the scalars over the configuration on 2 points here, this determines a Poisson bracket because these rules here, antisymmetry, Jacobi, and Leibniz rule, allow you to extend, especially the Leibniz rule, allow to extend anything with this, which is defined on the generators on the products. So by Leibniz rules, you define something on the generators and you extend it everywhere. So it's enough to give something which is just antisymmetric, a bundle map on the generators to have a Poisson structure. Okay? Then there are some remarks. The density bundle on the configuration space is a free symmetric algebra with respect to the Cauchy product, starting from the density bundle on M. I need it in order to perform some dual in the analytic sense. Okay, and so the conclusion is that I can now consider the symmetric powers with respect to both tensor products on the dual of this E bundle. I take the Hadamard tensor product with the density on the configuration space. This is formally the functional dual in the analytical functional sense of symmetric tensors. And I call this my Poisson bundle. This is the good candidate whose sections describe the kernels of multilocal products for observables. And so we need to go to sections. So sections of such bundle are, in fact, a collection of sections of every true vector bundle on the configuration on K points. Then we need distributions. Okay, distributions can be defined with values in vector bundles. We know, so we take usual distributions. We start with regular distributions, which are just sections with compact support and all smooth sections. And then we extend them by taking the continuous dual, the topological dual of the space of sections, and we get distributions with values in this functional dual vector bundle. So everything is well defined. And so the theorem is that if we take on the right-hand side the set of smooth functions and just usual distributions, then we get, if P is a bundle on the configuration space with the Poisson structure, then the sections and the whole set of distribution are Poisson algebras. Instead, because we took the diagonal off, we cannot preserve compacity. So the sections with compact support are not a subalgebra, and this is a problem. So we will need to go to the orbifold in order to have the complete picture of that. So the corollary of this theorem is that if we apply it to our best favorite Poisson bundle here, then with the Poisson bracket, which is given by this antisymmetric bundle map, we get on the section, on the smooth section and all the space of all distribution, a Poisson structure. Okay, so let me remark that taking an antisymmetric bundle map on this bundle here, the dual of E, it's the same as taking a smooth section on the 2-point configuration space with values in the antisymmetric Cauchy power on the original bundle. So this is just vector bundle theory, which is a regular distribution. So this has all the good properties to be a propagator, but from the bundle point of view, you only recover regular distributions, and usual propagators in QFT are not regular distributions, they are highly singular. So if we want to describe really QFT, we have to go to singular distribution kernels. They are not induced by bundle maps because they are distributional analog of bundle maps. Okay, so the claim is that the causal propagator is an antisymmetric distributional kernel, which yields Poisson bracket on the sections of this bundle. And there is a Poisson map, which is not injective, which is just the evaluation of distribution. So when you take a distribution with values in this Poisson bundle and you evaluate it on a certain field, you get exactly observables as defined by Kasia. Okay, in order to keep track of all possible sections here with values in these symmetric powers, one needs to introduce a kind of a formal exponential series of the field in order to have sum of all powers that can match with any possible section of this bundle here. Okay, so this, yeah.
So there is something that has been bothering me for a while, so maybe you know the answer. So when you go to distributions, right, then if you have, let's say, distribution in n arguments, and one of them is a Dirac delta, then when you integrate it, you have a distribution in n-1 arguments. And they both would give you the same functional. So in a sense, there are some identifications.
Yes.
Yeah, so the same functional can be given by these distributional kernels of arbitrary order, because I can stick as many delta distributions as there are. So I was wondering how you're describing that.
Sorry. Here are observables, so they are defined on E with values in R. What I'm saying is that there exists such a map, which is just the evaluation, so the integral over the configuration space of M. So this is the evaluation of distributions. Here we have a certain space of distribution on the configuration space with values in a certain Poisson bundle, okay? This map is not injective, so there is a kernel.
There is a lot of kernel.
There is a huge kernel.
Okay.
There is a huge kernel. So this diagram is the beginning of a whole story. What is inside here leads to higher structures, because here you have exact forms which clearly are in the kernel. So
Sure. Yeah, but also there is, as I said, the
And there are-
identification.
of course, there
Yeah.
are all possible identifications of these. So the identification you are talking about is even more extreme in the sense of singularities, because it means that you are kind of dropping a point.
Yeah.
So it's a reduction of this orbifold on its singularity.
Yeah.
And so just next slide will be the conclusion, and I will tell about this extension to orbifold.
Yeah, because that's an interesting object,
Yeah,
actually.
I will tell you. So in fact, this is the claim. So the claim is that we can define it, but so this map here is highly non-injective. And so the problem is also, what are these distributions here? So if you want to, so I put it as a claim and not as a theorem, because we are still working on really fixing what is this pattern of distributions. And I already know that we will need Bornologies because we cannot keep track of capacity. So from microcausal conditions, so Fredenhagen schools, Kasia included, we know that these sections should be with compact support, plus extra conditions on the wavefront set of its derivatives. So we cannot preserve compact support. So we tried to solve the problem with Bornology instead of topology. So Kasia knows that we have a school in Lyon with Johan Dabrowski, who was working on Bornology. So I don't want to go into the detail. It's a fascinating theory. Okay, we will need microcausal conditions for this distribution. It's not fixed. So the idea anyway is that on one side, things with compact support, either distributions or regular distributions, do not form an algebra. But since they have compact support, when I integrate, when I compute the distribution, I get something finite. So there is a well-defined map F going from such distributions to the set of observables. On the other side, I have a set of distributions and regular distributions which do form an algebra, but since they don't have compact support, the map is not well defined. So we have a divergent integral. And in between the two, there are universal properties of symmetric algebras, which tell us that there are algebras inside here, and we are exploring several algebras. So one of them, we have it here, but its extension to distribution doesn't work. So we are still working on this set of distribution. On the set of regular sections, we have it. We are still missing exactly this space. And I think we cannot really solve it without introducing again the diagonal. So I'm finishing. This is the last slide. Then there is just an appendix that I will skip. So the quantization, once this is done, the quantization is automatic because I already know algebraically in this category with these symmetric powers how to do this quantization here in the sense of a Drinfeld twist. I know it. In fact, it's already written, but it's not satisfactory until we don't know exactly what is the set of distribution, so it stands a little bit there. But in fact, the main problem is that we need to add the diagonal again to include it in the space of configuration. And so we get something which is a multi-configuration orbifold. And this is it's a tough step in this project. And it's, so there is a student, Haichao Nguyen, who is working on this in the second year. I hope that for next year, he will have the results of his thesis and we can go on. And then there are other ideas. So in fact, we found a double Poisson bracket. Double Poisson bracket was introduced by Vandenberg. It automatically gives R matrices. And so I'm really puzzled because R matrix is solution of a Young-Baxter equation. It means that the system is integrable. And this, I still don't know how to explain, but I'm in touch. So we are doing this with Maxime Ferron, who is a specialist of R matrices, integrable systems, because I'm puzzled. This comes out automatically, the structure of an R matrix from this algebraic structure. And then, so all this is related to the problem of finding multi-local observables in multi-symplectic geometry. It is not clear what it is. So the theory is stuck on this, on the definition of observables. So I think we know how to do it. And we would like to find the relationship with factorization algebras. And I know that Kasia was working on that, because I think simply that we have the bundles for which they have the sections. Okay, and then there are higher groupoid symmetries on which people are working. Okay, and then there is all this structure here to resolve, to get on-shell observables. So here, for spinors, nobody's working on spinors. If someone is interested, it's open stuff. And how to resolve on-shell observables, which means making a quotient here and reproducing this diagram on the quotient. This is also, for the moment, nobody had time to look at it. It's an open problem if someone is interested. Thank you very much.
Thank you, Alessandra. Any questions? I should say any more questions?
Oh, I just wanted to follow up. Now I understand what you're talking about. And on that question, I asked before, because we have this paper with Owen William where we related the factorization algebra picture to PQFT
Yes,
on the level of functionals.
precisely.
And then we wanted to do it on the level of the integrands. And the missing thing was exactly the fact that there is this infinite redundancy with these sections. So is that what this paper is addressing, or
Okay,
the one?
No.
No.
I think we really have bundles. So I think, in fact, here there is a bundle. So from my point of view,
But it's not the bundle that's the problem. I think it's the fact that distributional sections, right? There is this extra degeneracy in terms of describing an integral with an integrand that doesn't appear with the smooth sections, because you can always multiply by as many Dirac deltas as you want.
so this is the problem here concerns the singular foliation in the orbifold here, in the space of configuration.
I'm not sure. Okay, I will have to really try to do it. And then
So
see if I-
there are hints of this in a paper in a huge book, in fact, by Dreamfeld and I will have to find
Yeah,
it.
so I was thinking that maybe one should use run space, where you have all these like sub diagonals and sub things kind of together.
Precisely.
But okay, so this is also what you.
Yeah, so
okay.
this is contained the singularity. So this is exactly the topic of this PhD thesis.
The one that exists.
Yeah.
Okay.
Hi, Chow. Yeah. So you know, one of the students working on this is Sasha Miel. There is another one in Lyon now.
Okay, so
There are two.
I should read that thesis.
Yeah, okay.
Okay.
And that's why both of you wanted to know you. So they insisted very much that you come to
Well,
you.
looking forward to it.
So my question will be much more naive, going back to the beginning. So you symmetrized looking at configuration spaces. What if you anti-symmetrize? What, just out of curiosity?
We didn't consider this case because
Yes.
we didn't need it.
No, I know you didn't need it.
Yeah.
But do you anticipate what could that lead to?
I don't know if it's consistent.
Yes, maybe.
One should really check, because all the algebraic structure that I was hiding at the beginning, it's not trivial. One really has to check that the things are well defined after this question. So it's a long story. Yeah.
If not, let's thank Alessandra again.
Thanks a lot.